Hi, in this video we are going to test our AVL algorithm. So AVL is equal to an AVL. AVL that we have the insert, for example, 10. Then we are going to have the insert for the 20 and on the 30. First of all, I'm going to traverse. Or what's this? Oh, okay, I forget to implement the traverse method. So we just have a helper method again, these three traversals, so def traverse in order, it's going to get a node, and it's going to be the same as we have defined in the binary search tree section. So if node dot left child, it means that if the left child exists, then we just have to call this method recursively on the node dot left child. Then we print out this node, so node data, and if the node right child is not a none, then we just have to call this method recursively. So traverse in order on the node dot right child. Okay, and we have a helper method again, def, for example, traverse on a self, and if the root node is not a null, so self.root node is not a none, we just have to call the self.traverse in order on the self.root node. Okay, so let's call this traverse method, and I think that it's going to work just fine. Okay, something's not good. Okay, and basically it's true because after the settle violation method, of course, at the end we have to return with the node. So if it's not going to be unbalanced, then we just have to return with the node without modifying the structure of the tree with rotations. Okay, let's see whether it's working fine or not. Yeah, this is a right-right heavy situation, so we have to rotate to the left on the node 10. It's working fine. And the in-order traversal is the numerical ordering. What if we have the left-left heavy situation, 5, 4, 3? Then we should end up with a right rotation on the root node, which is the 5. Okay? Yeah, we rotate to the right on node 5. 3, 4, 5 is the numerical ordering. What if we have, for example, 5, 6, 7, and 6? It is the right-left heavy situation. We have a right, then a left rotation. So right and the left rotation. Yeah, right on 7, then left on the root node. It's working fine. What if we have, for example, 5, 3, and 4? It is quite on the opposite. We have the left-right heavy situation. So we have to rotate left on 3, then right on 5. So left on 3. Okay, because we have to save it. So, okay, we have some error. That's why it is a good programming practice to test the algorithm you implement. So rotate left on the 3 is working fine, but after that we are not able to rotate right on the root node, which is the 5, because object has no attribute right child, line 49. Okay, of course, sorry for that. Not right child, but right rotation. Or rotate right. Yeah, rotate right on the node. Of course, sorry for that. Okay, so let's see whether it's working fine. Yeah, we just have to rotate to the left on node 3, then on the root node to the right. It's working fine. So let's see, for example, the original example. So we would like to handle the situation when we insert items in a tree from a sorted array. So we have the 1, 2, 3, 4, 5, and 6. Let's see whether it's going to be balanced. CLS to clear the console. Yeah, it is right heavy situation. 1, 2, 3, 4, 5, 6. First of all, it's going to work fine as far as the traverse is concerned. And first we have to rotate to the left on the root node. It's going to be okay. Then we have to rotate on the 3. Then we have to rotate the whole on the 2. This is what we have been discussing in a theoretical section. It's working fine. So basically that's why it's very important to insert the node. It's going to be the same as we have seen for the binary search tree, but on every insertion we have to check whether we have violated the AVL properties. We have been discussing the 4 cases in the theoretical section. That's why we have these helper methods, the height and the balanced. This is how we are able to decide whether there is a left heavy situation or a right heavy situation. And then we have to make the rotations, which are basically just reference updates. So we just have to get the left child and set the left child, right child, and accordingly, and so on. So that's all about the insertion implementation. Thanks for watching.